All right, I want to give a quick overview on how to bias a common emitter amplifier. There are different types of amplifiers you can make with a BJT. When your input is on the base and your output is on the collector, the emitter then is common to both the input and output, and it's called a common emitter amplifier. There are common base amplifiers, common collector amplifiers, but in Lab 4, you'll be using a common emitter. Now, we need to bias it to make it work, so we're going to talk about what that means and why we need to do it. The BJT operates in different regions. We need to be in the active region for this to operate properly as an amplifier. So that's why we need to bias it. Our goal is to keep it in the active region. If we're in the cutoff region, then this is going to act like an open switch. There's no current flowing, and that would be a really poor amplifier. Our output would just sit at 9 volts. Okay? If we are saturated, then especially if we're in deep saturation, then this is like a short, and we just have this voltage divider of RC and RE. That's not a very good amplifier either. So we're trying to be in the active region. The other thing we need to do, or that we really want to do when we're designing this, is we want to think about something called headroom. So if this is our signal, that's our input, and we're going to be amplifying it, when we amplify it, if we have 0 volts and 9 volts, we want to make sure we're kind of in the middle of that. We wouldn't want to amplify and be centered up here, because this would cut off, it would clip. We can't go above 9 volts. And the same down here. If we're too low, then we'll just kind of clip, and pardon my messy drawings. So what we want to do is we want to figure out what our rails are. We want to figure out what is the highest value that Vout could be and the lowest value that Vout could be, and we want to design for this DC value here to be sitting at the center of those rails. Then we're going to have great headroom. And if it's not right at the center, you know, pretty close. So we already said that if we're in cutoff and this is an open switch, then we will have this no current flowing here, and our output will be sitting at 9. So 9 volts will be our upper rail. Let's go to a new page because this is getting messy. Okay, so we've got 9 volts as our upper rail. And what is our lower rail going to be? Well, if we're in deep saturation, this is going to act like a short, and we will be left with a voltage divider. So we'd have RE over RC plus RE times 9 volts. Okay, so now in order to get that value, we need to have some numbers here, not just RC and RE. For Lab 4, you guys are challenged with the task of designing an amplifier of 5 volts to volt. Okay? I am going to design one today to show you at 8 volts per volt. So you can get a feel for the process, but then be able to have the design problem of coming up with your own numbers. Now, our gain equation is roughly approximated by RC over RE. You will see that it doesn't follow that perfectly. There are definitely other things involved, but it's a good place to start. So I'm going to say 820 since we have that value in our kit, and I'm going to make my RE 100 ohms. So now if I plug my values in here, I am going to get about 1 volt. So the highest my output could ever be is 9 volts. The lowest my output could ever be is about 1 volt. And remember, if you have a gain of 5, your values will be a little bit different for here, which will give you a little bit different lower rail. So while I'm biasing my transistor, my amplifier, there's the 2 things I want to remember. I want to be in active mode, and I want to think about my headroom. So I'm going to shoot for trying to be about 5 volts. So let's jump over to LT Spice and design it. So I stuck in 820 here and 100 ohms here, and I am going to pick values for R1 and R2. And the best way to do this, first of all, remember these are going to act like a voltage divider, that we're going to make it so their impedance is not as big as the impedance looking in, so that we can think of them roughly as a voltage divider. So we're going to pick a value for one and then solve for the other. So I'm going to pick a value for R1, especially when you get to Lab 5 on your PCB. There's 1 slot for R1, and then there's 2 slots for R2. So if you pick R1 to be something that's a standard value, then it makes it easier. So I'm just going to say 12K. I could say 10K. I could say whatever I want. I could say 8K. You don't want to go too hot. I wouldn't want to do like 1 meg because then my voltage divider wouldn't start working as well. And I don't want to go too low here. And Lab 5 will be operating off a battery, and I don't want to draw too much power. So if I have 12K here, I need to figure out what voltage I want, what resistor I want here to get the proper voltage. So what I'm trying to do is I want to have a voltage drop here that might be 0.5 or 0.6. Then there will be a voltage drop across this resistor. And what we're trying to do is have the right amount of voltage or current coming through here, and then that will amplify, and there's going to be a current coming through here that's going to make this sit about 5 volts. So this is a bit convoluted. If you're biasing a common collector amplifier, it's much more straightforward. The common emitters, you're controlling this voltage to control this current to get this to sit at 5 volts, and it's a little bit of a pain. But I don't mind if you use LT Spice as a design tool. So let's come in here and we'll pick like 1 micro. It just needs to be something to block the DC. This is really important. This capacitor is going to block the DC of your input. Otherwise, all this work we're doing to get the appropriate DC bias will get messed up by whatever your input is. So make sure when you're doing an amplifier where you're setting up a bias that you can separate the DC of your amplifier from the DC of your input with a capacitor here. That's really a good idea. All right. So let's have an input sine wave, and I'll just say it's going to be 1 volt, and we don't care too much about the DC offset. Frequency, we don't care too much about that either. All right, so now we have a sine wave coming in, we have our capacitor here, and we're still left with the challenge of this guy. So let's come up with a rough number. If I want 5 volts here, I can figure out what I need to do. I'm going to come back to where I can write. Okay, so if I want 5 volts here, then I need to know 9 minus 5 is 4. So I want a 4 volt drop across that guy. So if I want 4 volts drop and there's 820 ohms, that will give me my current. Okay? So I can do 4 divided by 820, which is for about 5 milliamps. Okay, so I've got 5 milliamps. Now, that 5 milliamps will also be down here. Technically, it's a tiny bit different than 5 milliamps, tiny bit. Your IE and your IC are a little bit different, but for our purposes, they're totally close enough. So we've got 5 milliamps here, and then we had said this guy was 100. So that's going to be 100 times 5 milliamps is going to be 0.5 volts. Now we'll have some voltage drop here. We can say 0.5, 0.6, somewhere in there. And that's going to tell us this VB that we want. So we want our VB to be about 1 volt, somewhere between 1 volt, 1.2 volts. So that gives us a good feel. So we need a voltage divider where we're ending up here. And we know it's R2 over R1 plus R2 times 9. And we already picked our R2. Obviously, it would be easier to pick R1 in this example. I mean, pick R2 and solve for R1. But we're going to use LT Spice, so it's not very hard. So instead of solving that, I'm going to just eyeball it. So we want about 80% to 90% of the voltage drop to happen across this value, and we want about 10% to be left or 15% to be left. So I'm going to look at that and say, well, what if I make this 1K? Or I could be smart about it and say, let's just make it a variable. Now we can step through that and say, it helps if I have my fingers on the right keys. Here we go. Step, param, X. We could have a start value at 800 ohms, an end value at 1400 ohms, and step by 100 ohms. Okay, so now I am going to run my simulation, and I'm just going to do a transient. So we'll just let it run for, I think I said 1K, so I'll just say we'll just do a few periods. And we'll run this and see what we get. We want to see our V out. Ooh, so I'm looking at this and I'm saying, first of all, I'm probably a little bit too big on my input. So I'm going to change my input because I am hitting my top and my bottom. Right now it's just giving me current because it still thinks I'm trying to pick that. Okay. So let's make this amplitude smaller. We'll run it again and we'll look at this output. So I can look at this and I can say, well, my bias is no good because I'm in the active region here, 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 but here I'm cut off. All of these, when I hit 9 volts, I'm cut off. So I am biased too low. I need more. I need a higher voltage here so that I'm not in cutoff. So if I need a higher voltage here, then I need to make this value bigger. So I need to change this, and it's not wanting me to change it. But anyway, hopefully this gives you the idea of the method that you can come in and you can see and you can adjust these things, because my goal would be for my center of my wave to be down at 5 volts and I'm up here at, closer to 7.8. So in summary, we are trying to keep it in the active region, which we're mostly in the active region right now, and you'll want to meet all your specs for lab 4, and you want to take a look at your headroom so you're not hitting your rails, that you can get a good output. And I hope this video has been helpful and that you do great on this lab.